Hello all, welcome back to Sri Sai Tech Edu YouTube channel, Read Lead Success. I am dealing with the subject Network Analysis and Control Systems. I have already uploaded Module 1 to Module 4 topics in my channel. If you have missed out, please do watch them. And in Module 5, I have already uploaded first chapter and second chapter topics. From this video, I am going to start the third chapter. Under third chapter, body plots, there are three topics. First one is basic factors of G of j omega, H of j omega, and general procedure for constructing body plots and computation of gain margin and phase margin. In this video, we will start with the topic basic factors of G of j omega and H of j omega. First, we will see the main basics of body plots. The introduction. Body plots is nothing but logarithmic plots with two parts. Logarithm plots with what? Two parts. That is magnitude in dB vs frequency omega, phase in degrees vs frequency omega. Magnitude in the terms of decibel, which is with vs frequency, and phase in degrees with frequency. These plots with two parts, the logarithm plots with two parts, these two parts is called what? Bode plots. Frequency is plotted on what? Log scale. Frequency is plotted on log scale. Advantages of Bode plots are convert multiplication or division of magnitudes into addition or subtraction. The multiplication or division is converted into what? Addition or subtraction. Wide frequency ranges can be plotted on the same graph. Wide frequency ranges can be plotted on the same graph. Wide range of frequencies can be plotted. It means. So, semi-log sheet has y-axis linear dB or degrees, x-axis logarithmic, that is frequency. Straight line asymptotes give quick approximate plots. Straight line asymptotes will give quick approximate plots, whereas determine absolute and relative stability of system. Bode plots will give the absolute and relative stability of the system. When it is used to, the Bode plots is used for stability, analyze stability, design the control systems, approximate transfer functions when analytical methods are hard, to approximate the transfer function when analytical methods are hard. So, perform frequency response tests, then draw Bode plot. We can perform frequency response test and then draw a Bode plot. To express magnitude G of j omega and H of j omega in dB, what we can do? Use the formula magnitude dB is equals to 20 log G of j omega into H of j omega. If you use this formula, you can express G of j omega and H of j omega in terms of what? Decibels. That is nothing but magnitude. The basic factors of G of j omega and H of j omega. These are the basic factors which are mentioned here. That is 12 basic factors are there. We will study one by one clearly. First one, gain K. Gain K. K is what? We know that it is open loop gain. Okay. A number greater than unity has a positive value in dB. A number greater than unity has a positive value in dB. See, means it is greater than positive value. Nothing but greater than the unity has a positive value in dB. Right. While a number smaller than unity has a negative value. If K is greater than unity, it is what? Nothing but it has positive value. Okay. While a number smaller than unity means K is less than unity, it has negative value. Okay. The log magnitude curve for a constant gain K is horizontal straight line at magnitude of 20 log K dB. Okay. 20 log K dB. Okay. When K is constant. Okay, the phase angle of the K is what? 0. The phase angle is 0 and the magnitude will be 20 log K for this value. Okay, the phase angle of K is 0. So the phase plot is straight line at 0 degree. The effect of varying the gain K in transfer function is that raises or lowers the log magnitude curve of the transfer function by the correspondence constant amount, but it has no effect on the phase curve. Figure 7.17 shows Bode plot of constant gain K. Okay, see what it is, what they are telling is if K is greater than 1, it has a positive value of dB, that is plus dB. If it is less than 1 and greater than 0, then it is what? Negative dB it is. If it is equals to 1, it is horizontal and it is a constant, then it has magnitude of 20 log K dB and its angle, phase angle of gain K is what? 0. So drawing this, you can easily explain what is gain K. Second factor, pole at the origin, integral factor, that is 1 by j omega. Pole at the origin, if the pole is at the origin. Pole at origin, integral factor 1 by j omega. The logarithmic magnitude of 1 by j omega in dB is 20 log K we should do. So 20 log K is what? 1 by j omega at the origin. You will get what? Minus 20 log omega dB. Minus 20 log omega dB. Okay. So 1 by, when what? When omega is 1, if you take, when omega is 1, you will get 1 by j omega as minus 20 log 1, 0 dB. When omega is 0.1, then you will get what? You will get as plus 20 dB. And for omega equals to 10, 1 by j omega will be what? Minus 20 dB. Okay. So in this way, you need to take the omega values so that you can plot it easily. See, when it is 0.1, it is what? It is plus T20. Okay. And when what? When it is omega equals to 1, it will be 0. And when omega equals to 10, it will be minus 20 dB. Okay. The slope of this need to be what? The slope of that is what? Minus 20. Minus 20 dB by decade. Okay. This slope is 20. Okay. Then, so if the magnitude of minus 20 log omega dB is plotted against omega on a logarithmic scale, it is a straight line. Here it is a straight line with a slope of minus 20 dB by decade. So passing through the 0 dB line at omega equals to 1 radians per second, because minus 20 log 1 is what? 0 dB. Log 1 is 0. The phase angle of 1 by j omega is constant and equal to what? Minus 90 degree. Okay. Figure 7.18 shows the Bode plot of 1 by j omega. Third factor, multiple poles at the origin. A single pole we have seen, one pole at the origin, and now multiple poles at the origin. There are multiple poles. Then 1 by j omega whole power n. The log of magnitude of 1 by j omega whole power n will become what? Minus 20 log omega power n it will become. Okay. So minus 20 n log omega. It is in the form of log m power log a power n, that is m log a you can write. So minus 20 n log omega you can write. Okay. When you should now again substitute omega equals to 1, you will get 0, omega equals to 0.1, you will get plus 20 n dB, and omega equals to 10, you will get minus 20 n dB. Same way what you will do, you will put at 0.1, you will get plus 20, at 10 it is minus 20, and 1 is 0. Okay, the slope will be minus 20 n dB by decade. So again you see here, it is the phase angle of horizontal, that is 0 degree. Okay, then the phase angle constant is equals to minus 90 degree and this shows the Bode plot of multiple poles at the origin. Same, no, second and third look same, but it is n. N is number, there are multiple poles. If there is no n, only j omega, then it is single pole. 0 at the origin. Derivative factor. Okay, when it is 0, it is. See, pole at origin, it is 1 by j omega, it is integrative factor. Now here it is differentiating, that is derivative factor it is called. So the log magnitude of j omega will be 20 log j omega, 20 log omega dB can be written. Okay, then 1 omega equals to 1, and omega equals to, as we know here j is nothing but about complex number, that is I is nothing but equals to 1. So you can write 20 log omega dB. So while omega equals to 1, what you will get? You will get 0 dB, and for omega is equals to 0.1 you will get minus 20, omega equals to 10 you will get plus 20 dB. Same way for the same like for the poles, how you will do? 0.1 it will be minus 20, 10 it will be plus 20, and 1 will be 0. And if you see this time the pole comes, slope comes this side, so it will be plus 20 dB by decay. Now you should write plus 20 dB. If the slope is like this, see it is here slope is like this, so plus 20 dB. If it is like this, then it is minus 20. So plus 20 dB decay. Okay, then so the log magnitude curve of 20 log omega dB plotted against omega on a logarithmic scale is straight line with slope of plus 20 dB decay passing through 0 dB line at omega equals to 1 radian per second. The phase angle g omega is constant and equal to what? Plus 90. So now it will be plus 90, not minus 90, plus 90. The body plot is shown here. Same way, multiple zeros at the origin. So it will be j omega power n. Same way you will write 20 log j omega all power n. So 20 n log omega, omega equals to 1, omega equals to 0.1, omega equals to 10. Same way you will draw the diagram for the border plot. Again in the same way what you will get, that it is constant and equal to plus 90 n degree. Okay, the same way for the poles and zeros. Then factors of the form k by j omega whole power r. Factors of the form k by j omega whole power r. The log magnitude of the factor, how we will do? 20 log of k by j omega whole power r. So then it becomes what? Minus 20 r log omega plus 20 log k. How this has come is, see how this has come is, first if you see here it is in the form of log m by n, that is in the form of fraction. When if it is in a division form, what you can do is log k minus log, you can minus it, log j omega whole power r. So this log k will be log k only. You need to multiply this into 20 anyways. 20 into, so 20 into log k will be log k itself, and this will become what? R log a power m, m log a, r log omega can be written. Okay, so it is written as what? Minus 20 r log omega plus 20 log k. 20 is multiplied inside. So this is the way it is written. Then when again you should put omega equals to 1 and omega is equal to 0.1, omega equals to 10. Using calculus, if you directly calculate, you can get as 20 log k dB. See, omega equals to 1 if you put here, when omega is equals to 1 if you put here, what happens? What you will get? Minus 20 r. Log 1, it is 0, so you will left with 20 log k. When omega equals to 0.1, what you will get? 20 r plus 20 log k. Okay. Then when omega equals to 10, what it happens? Minus 20 r 20 log k. So how you will write? When 1, it will be plus, when it is it will be plus side, and when it is 0.1, what you will get? Minus 20 r plus 20 log k dB. Okay, it is minus side. This will be what? 20 log k dB. Like this you will get the slope. Okay, like this you will get the slope. And this will be what? At 1 it is 20 log k. See how it is written is, first don't consider this. Okay, first just consider when omega equals to 1. What you got? 20 log k. This will be the point. 20 log k, just think. Then 0.1, it is again positive, more than this. Add of 20 r. when it is omega equals to 10, it will be what? Minus, very end. Same here, this point, end. So to draw this line, it will be meeting some point. Now that point, how they have found is, see, 20r log omega. 20r log omega equals to what? 20 log k. 20r log omega. How they have equated this is, if you see, when you have done, you got with some equation like this, no? When you have put 20 log kdb, when you did, you got some equation, no? This how they have took, they took this 20r log omega one side, that is equals to 20 log k they have took. So what it means, that 20r log omega equals to 20 log k. So from this 20 log and 20 log will get cancelled. Omega is equals to what? K power, this r, if you go right side, it will become k power 1 by r. So this is the meeting point. So this point is what? K power 1 by r. So the angle contribution of the factor k is 0 and of the 1 by j omega whole power r is minus 90 degree r at any frequency. It becomes minus 90 degree 90 r degree. The phase diagram is simply horizontal line angle at minus 90 r degree. So figure 7.20 shows the Bode plot of this one. Factor 7. First order pole on the real axis. First order pole on the real axis. What is that? 1 by 1 plus j omega t. First order pole. So this is of the first order pole. So if you take log 20 log k, this is the k, no? If you substitute, then what you will get? What you will get? This is written as how? 20 log 1 by root of 1 plus omega square t square. So this, if it is gone up, then it becomes 1 plus omega square t square whole power minus 1 by 2. So it is in the form of log m power a. So it can be written as a log m. A log m, that is minus 10. So 20 by 2 is minus 10 log of 1 plus omega square t square. For low frequencies, omega less than 1 by t. Okay, the log magnitude may be expressed as what? 20 log of 1 by 1 plus j omega t, that is minus 10 log 1. When it is less than 1 by t, less than, it becomes 0 dB. Thus the log magnitude curve at the low frequency is constant 0. Then it is, if it is omega is greater than the 1 by t, then it can be written as minus 10 log omega square t square. So it becomes minus 20 log omega t, that is minus 20 log omega minus 20 log t. Okay, so this is an approximate expression for the high frequency range. The error in log magnitude curve of 1 by 1 plus j omega t for 0 less than omega less than 1 by t is given by what? This equation. Therefore, the error at the corner frequency omega equals to 1 by t is minus 3 dB. Then the error at half the corner frequency, that is 1 by 2t, is what? When you should put in the place of omega as 1 by t and omega as 1 by 2t. Then you will get minus 1 dB. Then if it is between 1 by t and infinity, then it will be what? Minus 10 log 1 by 1 plus omega square t square plus 20 log omega t. Therefore, the error at the corner frequency omega equals to 1 by t is what you got as minus 3 dB here also. Then 2 by t you will get minus 1 dB. So, thus the error at 1 octave. Thus the error at 1 octave below or above the corner frequency approximately equals to what? Minus 1 dB. Similarly, the error at 1 decade below or above the corner frequency is what? Minus 0.04 dB. So, the phase angle phi of the factor 1 by 1 plus 1 j omega t is phi is equals to minus tan inverse omega t. At corner frequency at t 1 by t, what you will get? 45 degree. And when phi equals to 0, then phi will and at infinite frequency phi equals to minus 90. At half corner frequency, when omega equals to 1 by 2t, what you will get? Minus 26.6 degree. When it is 1 by 10t, it will be minus 5.7. Yes, just substituting in the omega place. In omega place, if you put 2 by t, you will get 60 minus 63.4. When it is 10 by t, and if you substitute in omega, you will get minus 84.3. An accurate smooth phase curve can be drawn passing through these points. Shows the Bode plot. If you see here, all the points are plotted here, and this is nothing but the Bode plot. 45, 26, like that, 84.3 here, and 63, minus 63.4, and minus 5.7 somewhere here. Like that, all the points are plotted here, and this is the graph shown. Next, eighth factor, multiple poles on the real axis. Same way the previously what we did, no, same way 1 by 1 plus j omega t whole power n. Again you will do in the same way, 20 log you will get, but in the place of minus 10 log, the n is added extra because it is whole power n. So less than 1 by t, greater than 1 by t, again you will find. Okay, so the magnitude plot of 1 by 1 plus j omega t whole power n can be approximated by two straight lines. One is the straight line at 0 dB, and the other straight line at the slope minus 20 n. This is the minus 20 and dB by decade for the frequency 1 by t less than omega less than infinity. The corner frequency omega c equals to what? 1 by t, and error at the corner frequency is minus 3 and dB. So the phase angle of the factor varies from 0 to minus 90 degree n. 0 to minus 90 degree n, as omega is varied from 0 to infinity. The phase plot is the curve through minus 45 n degree. It will come from the 45 n degree at omega c. At exactly omega c, the curve moves like this from the omega of minus 45 degree n. So the figure shows the Bode plot for multiple poles on the real axis. Ninth one, first order 0 on the real axis. First order 0 on the real axis. How? 1 plus j omega t. Same way you will write 20 log 1 plus j omega t. Then minus 20 log 1 by 1 plus j omega t, you can write this in the form, right? You can write, can change this into division 1 by 1 plus j omega t by making it minus. Okay, so angle of 1 plus j omega t is tan inverse of what? Omega t. So that can be written as minus angle 1 by 1 plus j omega t. Same way. So the Bode plot of 0 factor 1 plus j omega t can be drawn in the same manner as for the pole factor, but with a slope of plus 20 dB by decade and a phase angle of plus tan inverse omega t. So the magnitude plot of 0, 1 plus j omega t can be approximated by two straight lines. One is the straight line at 0 dB. This is the 0 dB. When it is 0 less than omega less than 1 by t, and the other is a straight line at slope t, 20 dB by decade, the frequency omega t less 1 by t less than omega less than infinity. The two straight lines are the asymptotes of the exact curve. The corner frequency is at what? 1 by t. The phase angle varies from 0 to plus 90 and it touches the the corner frequency at 45 degree. Okay, and the correction, dB correction will be plus 3 dB. Previously it is minus, here plus, and plus 1 dB at half and double corner frequencies. Multiple zeros on the real axis. Same for like the previous one. What you will do? You will write in this way. Just the n will be added to it. So for less than omega less than 1 by t, you will get 0 dB. Greater than 1 by t, you will get 20 n log omega t. And if you see here from 0 dB and there is a plus 20 n dB by decade and the corner frequency as 1 by t, and the degrees will move from what? 0 to 9 plus 90, where the corner frequency is touching at plus 45 n degree. Same way, same like the previous, it is multiple zeros. Quadratic poles and quadratic zeros. Okay, here it is 1 by this equation, here is that's the equation. Okay, so complex conjugate poles, that is control system, often possess quadratic forms of the form. Quadratic forms are there in the control systems. That is 1 by 1 plus 2 xi j omega by omega n plus j omega by omega n whole square. The log magnitude of this you will get as like this. Okay, so when omega is less than omega n, the log becomes what? 0 dB. When it is greater than omega n, then you will get minus 40 log omega by omega n dB. So the high frequency asymptote is a straight line having the slope minus 40 dB by decay. The high frequency asymptote intersects the low frequency asymptote at omega equals to omega n on the 0 dB. This frequency omega n is called corner frequency. That frequency is called what? Corner frequency. These two asymptotes are independent of the value of xi. Near the corner frequency omega equals to what? Omega n. A resonant peak occurs. The damping ratio xi determines the magnitude of this resonant peak. The error between the actual magnitude and the asymptotic approximation is given as follows. When it is 0 less than omega less than omega n, the error will be what? 0. Okay. When it is omega n less than omega less than infinity, the error will be what? Again equals to 0. See, these two are different equations which is equals to 0. From the above expressions, it is seen that the error is a function of psi and the normalized frequency u equals to omega by omega n. The error versus omega by omega n curves for different values of psi are plotted here. See, these are the different values plotted for different values of what? Psi. See, this psi value is changed so that values of xi are shown. The corrected log magnitude curves for various values of xi are shown in this figure for both 1 by 1 plus and this is error in dB versus normalized frequency for asymptotic, and here it is Bode plot. The phase angle of the quadratic factor is given by what? Tan inverse minus tan inverse of the this two xi omega by omega n and omega n 1 minus omega by omega n whole square. This the phase angle is a function of both xi and omega. Okay, so the phase angle plots for various values of xi are given in what? Figure 7.25, which we have seen previously. For all those poles, omega equals to what? 0. The phase angle will be 0. So the curves become sharper in going from the low frequency range to the high frequency. If you see in that diagram, from low frequency to high frequency, the curve becomes very sharp. Okay, so to high frequency range as xi decreases until for xi is equals to 0. The curve jumps discontinuously from 0 down to 1 minus 180 degree at omega equals to omega n. So the plots of 1 plus j2 xi omega by omega n minus omega n whole square, that is complex conjugate zeros, are similar to the plots of complex conjugate poles. This and this are similar, what they are telling. Okay. So this completes the basic factors of g of j omega and h of j omega. So 12 factors are there. They may ask in exam what are the factors of g of j omega and h of j omega. So please do practice them. Then you have next general procedure for constructing Bode plots and computation of gain margin and phase margin, which we will see in the next upcoming videos. In this video, we completed basic factors. I am stopping the video here. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.